Functions. Functions. Just relating one function or one variable to another. That's all a function is. That's all a function does. So here, they talk about it such as a rule of correspondence in a relationship. In mathematics, equation formulas represent relationships. For instance, we have this here, where I earned on $1,000 for 1 year is a relation to the annual interest rate R by the formula I equals 1,000 R. So we can define things. We can create equations to model things that we expect are kind of represented in a real world kind of situation. And we define a function f from a set A to a set B is a relation that assigns each element of x in A to exactly one element in y, or one element y in B. The set A is the domain of the function f, and set B is the range of the function. And we call this, for one element attached to 1, is 1-to-1. It's a 1-to-1 function. And we can get more into that in some of the upper level math classes that we don't offer here that you can actually take in college, start going in more detail in that and talking about injective, surjective, and bijective functions and how the domain and range relate to each other and work together. But we're not going to get fully into that. This is a picture. Function. We have ordered pairs. Each element of A must match an element of B. Some elements in B may not be matched with any set 1 in A. And we can have some, 2 or more elements in A may match to the same B. That's fine. It just means we have different X values going to the same Y value. And that's perfectly fine. The only thing we cannot have is an element in A cannot be matched to 2 different range values. I can't have one X value to 2 different range values. That's our vertical line test, going straight up and down. If we can draw a line straight up and down and it crosses the graph in more than one place, it is not a function. We can still have an equation for it, but it's not a function. Verbally, by a sentence that describes how the input value is related to the output value. Numerically, by a table or list of ordered pairs. Graphically, by points on a graph in a coordinate plane in which the horizontal axis represents the input values and vertical represents the output values. Algebraically, by an equation in 2 variables. Determine whether you must input the matches. Kind of really, the vertical line test is what really helps determine if a function is a function. One of the other big ones is, well, it'd be helpful if I had a pen, is y by itself. Does y have any powers attached to it? Because if it doesn't, then there's a good chance it's a function. Because if we could say y equals x squared plus 2, that's fine. That is a function. This is not. Y squared equals x plus 4 is not a function. What I'm going to do here is actually graph it. Let's see if it'll give me a keyboard. I'm going to have to, yep, I'm going to have to type it out. So y shift equals x. I don't know if that's the exact equation I wrote, but the main thing is y squared. Can we draw a vertical line and cross the graph at more than one point? Let's say x. Well, that's not what I wanted. Even a crooked line, it crosses at more than one point. Shift. Almost. Let's give it one more try. X equals 3. Does it cross the graph at more than one spot? Well, yeah, it crosses in 2 places. Yes, that blue line, that's our vertical line test. I can draw a vertical line. It crosses it at more than one point. It is not a function. It is an equation. It's just not a function. So one of the big things, if y has a power, a absolute value, if we have stuff attached to y other than like plus 4, minus 4, times 2, it's most likely not going to be a function. Desmos is a good place to go to do that, to kind of check it. One other kind of, not so much rule of thumb, but kind of, if you're having to take square roots or powers, apply powers to some of the functions, there's a good chance it's not a function, but you can always graph it. Desmos is one good place to graph it, especially if, let's see here, shift 6, 2. Again, this here is not a function. It's an equation, but it's not a function, because we can draw a vertical line and cross it twice. And I don't think I need to dwell too long on this here, determining if it's a function, if it's not a function, because it's just input values, output values. Here, 2, 10, 2, 11. This is not a function, because we have one x value going to 2 y's. Doesn't work. But I can have one x, or I can have different x's going to the same y. That's fine, because we have it here. These two different x values are going to the same y value. That's fine. Does this make sense? And kind of this is a passing thought. It's almost, if asking a question and giving you two different answers for the same question, we don't like that. But it is possible to ask two different questions and get the same answer, and we're more fine with that. Would you all agree with that? Because it's sometimes frustrating, you ask two different questions and get the same answer. But it's not as frustrating you ask one question and get two different answers. That doesn't work. Y equals x squared is a function. We can draw a straight line up and down. The domain of the function is a set of all inputs and output values. Scientific or function notation. X is an input. F of x is an output. X is what we put into the function. F of x is what we get out. X is the independent, or the independent variable. F of x is the dependent. X is what we change. F of x changes dependent on what x is. The symbol f of x reads as, well, as I've been saying it constantly, f of x. And we have this here. Now, we could plug functions values in. Again, I don't think I broke any new ground here. Because if we say f of -1, f of 0, f of 2, all we're saying for x equals -1, we have f of -1. So every x in the function, we replace it with -1 and simplify. Or with 0, plug it in, simplify. Or with 2, we plug it in, simplify. And we can have all these here. We can have multiple. We can have x. We can have t. We can have g of s. It doesn't matter. And we have these here. Now, a function defined by two or more equations over a specified domain is called a piecewise function. So we have this here. Now, the way we evaluate these or work with these here is that we plug in the value for the given function based off if it qualifies with our inequality statements. So what this is saying, that f of x is equal to x squared plus 1 if x is less than 0. So any value of x that's less than 0 works for the first part. So if we say f of -1, well, since -1 is indeed less than 0, we're not plugging it into the x minus 1. We're plugging it into the x squared plus 1. And then we can simplify from here. -1 squared is 1, and 1 plus 1 is 2. So for us here, f of -1 is 2. Now they told us the next one was f of 0. Well, f of 0 does not satisfy the x is less than 0. It satisfies the x is greater than or equal to 0. So we have to use x minus 1. So we replace x with 0. 0 minus 1 is. So f of 0 in this case is -1. That's it. And the last one, f of 1. Would we use the top equation or bottom equation? Is 1, now, looking back at these here, which one makes it be true if I plugged 1 in for x? It'd be the bottom one, because 1 is greater than or equal to 0. Because when we plug it in, we're looking at this first to see which one of these statements, 2, 3, 4, makes it true, because 1 is greater than or equal to 0. So again, for this one, we're using x minus 1. So we have 1 minus 1. So f of 1 is 0. Does that make sense? Yeah, because it's all depending on what the value of x is when we plug it in. Now, the domain of most functions is going to be all real numbers. For absolute values, quadratics, higher degree polynomial functions, it's going to be all real numbers. The only ones that we start having restrictions is rationals, when we have x in the bottom of the fraction, or with radicals. Then we have some restrictions, because here there are certain values that could make the denominator be 0, and they have to be removed. And radicals, even roots, because what's inside the radical cannot be negative. It can be 0, it just cannot be negative. So we have to remove those from the domain. But I'm not going to be too focused on those there. If we have time, we'll go over the distance formula later. But that's actually it. Questions on this here? I know we went kind of fast through this. (11 through 29 odd). So 11 through 17 odd, all you're doing is determine whether the equation represents y as a function of x. Determine if it's a function. You're saying yes, it's a function, or no, it's not, on 11 through 17 odd. 19 through 29 odd, find each function's value if possible. So they'll give you some different values you're plugging into the function and telling what that value is, if it's possible. There might be a few where we cannot actually get a value, and some of them are going to be expressions. You're actually plugging in a number and a variable and simplifying. If you do have questions on that, let me know. I will answer those and help you out. 35 and 37, find all real values for x for which f of x equals 0. Solve it. 35 and 37, you're just solving for the value of x. Sorry, 35, 37, 41. Solve for the value of x. And that's it. And luckily enough, you have the entire rest of the class period to work on this.